Right, EKC. And basically we're just taking the model with substitutable inputs, but we're now saying that the price of an input, the natural resource input, is made up partly of the extraction cost, which was fixed, but partly of the social cost of pollution, the damages caused by pollution, or the marginal damages caused by pollution. And crucially, we say that the marginal damages caused by pollution are some percentage, if you like, of production. So pollution effectively knocks out a percentage of production. So we've got ALL to the 1 minus alpha R to the alpha, that's our baseline production, but then we lose e to the minus p to the phi. A fraction. We only have we have a fraction e to the minus p to the phi left of this. So for reasonable values of p, this is going to be like 0.99 or something. So we have 99% of it left, but we lose 1% due to the pollution. And we have growth driven by growth in AL and L. And where is R coming from? For simplicity, we just say that we have perfectly substitutable inputs indexed by J. And where's pollution coming from? It's flowing directly from the use of the inputs. J equals 1 to n psi j dj. Psi. Okie doke. So what happens in this model? Well, how much goes to the consumers? If we call that Z, it's ALL to the 1 minus alpha, R to the alpha, which is the sum of dj to the alpha, e to the minus sum of psi j dj to the phi. So that's your net production, and then we have to subtract the widget inputs to the extraction sectors, wj dj. So that's consumption actually, isn't it? I don't know why I didn't call that C, but whatever. So the social planner is surely going to try and maximize consumption, isn't she? Why don't I just call this C? Why did I call it Z? I don't know. Okay. So let's take the first order condition in D1. What do we get? Well, this is like D1 plus D2 plus D3, blah, blah, blah. Okay. So we got a thing going on here. And we're going to do this like economists, right? So we've got alpha times all this divided by, if we differentiate the outside, it's alpha times everything divided by R, isn't it? Because this is R to the alpha. So we've got alpha times everything, which is Y, divided by R, or sum of dj. Okay, and then when we differentiate the inside, we've got D1 plus D2 plus D3, blah, blah, blah. Well, actually, we're just stuck with 2 technologies. Yeah, sorry, we've gone down to 2 technologies. So we can take these sums away and just write D1 plus D2. Then when we go, so I don't know why don't I just write like that? When we go, so alpha times everything divided by d1 plus d2 instead of an alpha minus 1. Then we go inside and differentiate and we just get 1. So that's that one. Then we've got this term with a minus sign. So we've got blah 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 equals 0. We've got a minus sign. So why don't we go equals and shift it over. d1, w1. So we just have a w1, don't we? But then we've got this term. Okay. How are we going to differentiate this? Wow. Why did I define damages in this tricky way for you? We could have done like a 1 minus p or something, which I think I do in the exams, but whatever. Let me think about how to explain this differentiation to you. Okay, let's give this a go. So I'm just going to do a box here, which I'm going to rub out in a while. Let's just say, like, x is e to the minus this lot, okay? I'm just making up this x terminology here. But then let's call this lot q. So let's say x is e to the minus q, where q is that sum da 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 to the phi. Okay, so then what is dx by dd1? It is dx by dq, dq by dd1, okay? That's the chain rule or the product rule or whatever it is. I never remember which is which. And what's dx by dq? It's just minus e to the minus q, isn't it? So it's minus x. Doing it like economists. And what's dq by dd1? It's phi times that lot to the phi minus 1. We're not doing it like economists anymore. And then we go inside and we've got a psi 1 d1 psi plus psi 2 d2, and differentiating with respect to d1 we end up with a psi 1, don't we? Okay, so dx by dd1 is minus x phi psi 1, and what's this? That's p, isn't it? P to the phi minus 1. But then it's times this lot. And x is just this, times this. So we end up with the full result is minus y, which is this times this, times phi psi 1 p to the phi minus 1. Okay, and then we're going to take it over and the minus sign will disappear. We have this minus w1 minus this equals 0. Took them over. So we have w1 plus, we've taken it over, y phi, oh actually I'm going to put the y at the end, phi p to the phi minus 1 psi 1 y. Okie doke. So that's the first order condition for D1. And by symmetry, the first order condition for D2 must be alpha y over D1 plus D2 equals W2 plus phi p to the phi minus 1 psi 2 y. Whew. And this is basically saying the marginal benefits of using this stuff is the contribution to production is equal to the marginal cost, which is the cost of digging it up and the pollution costs. And that has to be true. If they're both being used simultaneously, that has to be true for both. But of course it could be that only one of them's used, and then only one of these will hold, and the other one is at a corner with 0 used. Okay, I'm going to pause there for a sec. Okay, as Douglas Adams might have said, we're home and vigorously toweling ourselves off. Okay, we're not quite there, but we're almost there actually. We've done the hard work. To get our heads around this, the first thing we can do is just imagine, forget about input 2. It could be that it's both more expensive and more polluting. Big up W2, big up Psi 2. So you're only ever going to use input 1. What happens? Well, imagine Y is very small, because AL is very small. Then this whole lot is going to be small, and you've basically got alpha Y over this is W1. So what's that like? Well, we're just back in a standard DHSS kind of model. It's the sort of DHSS model with constant extraction costs that we did way back, isn't it? Where the extraction is going to track growth. And, yeah, we can drop the D2 because that's 0. We've got alpha Y is D1, W1, D1. Extraction tracks growth. Pollution is linked to extraction. Pollution tracks growth. But then imagine, as that happens, AL gets bigger, Y gets bigger, this term gets bigger. Imagine much later, this term has got huge compared to this. So the extraction cost is trivial compared to the damage caused by the pollution from the emissions. And this is getting close to being the case for things like coal today. The damage costs are like more than what it costs to dig the stuff up. Certainly if you don't catch the sulfur and so on. Well, not just more, a lot more. Okay, so then we've got alpha Y over D1, because remember we're saying, we're forgetting about D2, it's 0. Alpha 1 Y over D1 is phi, P to the phi minus 1, psi 1, Y. So then the Y's actually cancel out, don't they? And what's P? P is just psi 1 D1, isn't it? So things end up cancelling out pretty nicely, and you end up with P is alpha over phi to the 1 over phi. You basically end up with a P to the phi is alpha over phi. That phi ends up under this alpha. Everything else cancels out using the definitions and so on. So then you're in the case, here pollution is constant, which means that D1 is constant, input use is constant, which must mean, again, thinking back, way back to DHSS, that the pollution price is tracking the growth rate. Which makes total sense, because, remember, pollution is knocking out a proportion of the production. And if the pollution is constant, there's a fixed proportion of your production being knocked out, production's growing, the marginal cost of pollution will grow, tracking that. So in the long run, when extraction costs are negative, you end up in a kind of balanced growth position with constant resource inputs, price of pollution tracking the growth rate of GDP. So the pollution path then, on a non-log scale for once, would look like this, and the GDP path would look like this. So this is resource use and pollution. Okay, but what do we actually see often? It's not this leveling off, it's more of a nosedive, isn't it? So why do we see this nosedive? That's when you switch from one input to another. So let's have a look at that after a very brief pause. Okay, so now we're saying we're going back to the baseline main case when there are two inputs. One of them is cheap, W1 small, but dirty, psi1 big. The other is more expensive, WT2 bigger, but not as dirty, psi2 smaller. When y is small enough, both of these terms are small, and it's the relative extraction costs that dominate. You're just going to use the cheapest resource, and you're here. But with growth, the weight of these terms increases, and at some point, as the second term starts to dominate, the second term is smaller for the second input, so at some point we're going to start switching to the second input. The switch is gradual because this phi is greater than 1. So as we start to switch, the amount of pollution declines, which means the marginal cost of pollution declines. So you get this gradual switch from, we gradually phase out the dirty input and switch entirely to the clean one. And then the limit are very high. Why? These are irrelevant, and we use purely the cleaner input. And if there are several inputs, we will like go through the inputs in order of increasing cost and decreasing pollution. And if there's a totally clean input, we will always adopt it eventually, according to this model. Okay, and that's the math. The interpretation we talked about in the lecture, and that's me done for this week.